So logistic regression, at first, some review. So logistic regression is a kind of similar to linear regression. But we have the so-called link function. So we have maybe we see this way. So we have link function f here. So the point is that if we think about the linear combination of predictors, then the one problem is that the range of this beta naught plus beta 1 x is from negative infinity to positive infinity if x is continuous variable in a real valued continuous variable. So that is not good because the basically we model the probability of response is equal to 1. Here the y is the response variable and which is in 0, 1. Oh, sorry. Yeah. So y is either 0 or 1. So we think about the probability that y is equal to 1. And that probability is between 0 and 1. So if the beta naught plus beta 1 x ranges from negative infinity to positive infinity, that's a problem. So the idea is that we use the function f, which maps the entire real numbers into 0, 1. So such a function should be like this. So this is basically the beta naught plus beta 1 x. Then we have, so basically, so maybe I would say z, and z is equal to f of beta naught plus the beta 1 x. So this range of the function is 0, 1. So that is the idea. And the beta, how to interpret beta naught and the beta 1. So in linear regression, it's easy. So suppose x increases by 1, what happens? The fitted value gets beta 1 larger. So it's not difficult to interpret. How about logistic regression? It's a little bit hard because x gets larger by 1, then the inside f gets larger by beta 1. But after we use this function f, it's not clear what happens. So if we think about around this range, maybe x increases by 1, then y value doesn't change much. Maybe the left-hand side, p of x gets larger by only 0.01. Maybe it gets from 0.97 to 0.98. But if original value of beta naught plus beta 1 x, x1 is here, then it gets larger by 1. Then maybe the change is much larger. Maybe probability comes from 0.5 to 0.8, for example. So it's not really easy to interpret the beta 1. Sometimes x gets larger by 1, then probability gets much larger, and sometimes gets only slightly larger. So yeah, still we can interpret, for example, whether or not beta 1 is significantly positive or significantly negative. We can say that in the same way as linear regression, but the exact meaning of beta 1 that isn't clear. And only way to interpret is through odds ratio. So if x gets larger by 1, then this odds ratio, the log of the odds ratio, log of the p of x over 1 minus px, that gets larger by 1. So the px over 1 minus px, So this is the probability of success over probability of failure. So if success probability is twice as large as probability of failure, then that is the 2/1, so 2. So it's somewhat intuitive. So it's not very intuitive, but still somewhat intuitive. So this ratio, log of odds ratio, gets larger by 1, larger by beta 1 if x gets larger by beta, when x gets larger by 1, then log of odds ratio that gets larger by beta 1. So that is only possible way to interpret the beta 1 directly. Okay. But overall, the interpretation of beta 1 is not easy. So the only sure thing is that the beta 1 is positive, then larger x means larger success probability. And if significantly positive, then the x is significant predictor. So that is the same as linear regression, but the interpretation of beta 1 itself isn't really easy. And here is just a simple case. I mean, the one variable case. One variable sometimes say we say simple. When we say simple linear regression, that means there is only one predictor. So if multiple predictors, then still the situation is similar. So we have additional terms, beta 2 times x2. Yeah. And logistic regression, because of this function f, the estimation isn't easy. So linear regression is somewhat optimized for optimization. I mean, the objective function is set so that optimization is easy. So because the loss function, the function to be minimized is a quadratic function. That is basically the easiest function to find the minimizer or maximizer if the principal coefficient is negative. So that is basically the easiest case to optimize the parameters. But for logistic regression, because of f, we have very complicated function of beta 0 and beta 1. So to maximize this function, basically we have to rely on the numerical method. But the one good thing is that this function is convex. I mean, the concave. So negative of this is convex. So optimization doesn't have the local maxima problem. So still, we can reliably estimate coefficients even if the dimension is high. Yeah, so here is the result. So that we regress the default probability by balance. Then you can see the higher balance significantly means the higher the default probability. And the balance gets 0.0055 larger, then log of odds ratio of default is gets 0.005 higher. So yeah, 0.5% higher. Yes, and percent does not mean anything, but the log of odds ratio gets 0.0055 larger. So higher balance, the higher default probability. So here success is default and failure is not default in statistical wording. Yeah, and the making prediction is similar to linear regression. So if you plug in numbers, so estimated parameters, then we plug in the new observation, the predicted value of new observation, then you can get the fitted value. So once you observe, for example, the balance of $1,000, then you can see what's the default probability. And I think that there was a quiz on this. So $1,000 balance, the default probability is the 0.576%. Okay, so I think that now we do the new things. So logistic regression, what happens when we have the qualitative predictor? So it's similar. Actually, it does not matter. So still, logistic regression works in the same way by using the dummy variable. So want to predict the default probability P of X by student status. x is equal to 0 and x is equal to 1. So what do you think? So being a student have the higher default probability or not? Actually, you can see that when in this regression model, the student, if the person is student and we don't have any other information, the default probability is higher and significantly higher with p-value 0.0004. Yeah, when I talked with a recruiter in the Capital One Financial, he said the student is actually good because usually their parents have relatively higher income, and yeah, so the default probability isn't really high. But actually, the student, if we don't have any other variables, then students have higher default probability. Yeah, maybe if we don't account for income, then of course the students study, so the income is lower, so that may affect the default probability. Yeah, so even if we have positive coefficient, that does not necessarily mean this causes higher default probability. So if we include the higher, I mean, other predictors, often it's not significantly positive. It becomes negligible, or sometimes even the other symbol, the other sign. Yeah. Yeah, so when I worked for the radiology department in Wisconsin, there are many educational data, and they just measure the performance of the students in some class, the pretty technological class, because that is radiology department, so they use a lot of the equipments. Then they compare the test score by gender, okay? And it sounds that in many cases, the male has a higher score in that specific exam or class. And often the project is measuring the effect of gender, but also accounts for other factors. And the fact is that the more male students come from engineering school, and that they are naturally strong to deal with those kind of technologies. So actually, the engineering students they perform significantly better in some radiology classes. But after we accounted for that, actually the gender isn't really significant factor. So that is natural thing. So it sounds that when we only introduce one variable, it looks significant. But actually, if we go into the details, then the result isn't really the same. So that's often the case. So here, if we only have the information on whether or not that person is student, then default probability is higher. But if we account for income or some other variables such as age, possibly that isn't really the case. Okay, so the students, yeah, so this is probably a little bit easier to interpret because we only have the one variable, and the student status only have the two cases, yes, then 1, and no, then 0. So this is the students, and this is non-student. So if student default probability, maybe within some certain period, is 4.3%. And if not student, the 2.9%. So the difference is about the 1.4%. So you can really see and interpret the result. Yeah, but if we have another variable, for example, another continuous variable, maybe the interpretation is difficult. For example, maybe the income variable, and we have the coefficient of maybe negative 0.003 or something, and the income, then we have to set the baseline income. Otherwise, we cannot calculate the direct probability, right? So if we have beta 2 plus x2, then we have to set some standard value for x2, so that we cannot really see we cannot say the student have the default probability of 4.3%. We have to set the standard scenario about the student's income. Yep. Yeah, but anyway, so the indicator variable, dummy variable, can be introduced for qualitative variable, the student.
Sorry.
Yep.
Sorry, Professor. I have a question about the subject.
Yep.
So when we want to predict the default probability,
yep.
I think the total probability should be 1, but we have the total probability is somehow about 6 or 7%, but I'm a little confused. So
I see. So
what's the other part of the probability?
Yeah, sorry. I think that my notation isn't really accurate. So this should be probability of default given student, the person is student, and the other is probability of y is equal to, oh, sorry. The student 0, 1. Yes, so y is equal to 1, x is equal to 0. Yeah. Yeah, you're right. So I think this notation is not correct. So given the information that the person is a student, the default probability is 0.04. Given the information that the person is not a student, then default probability is 0.029. So sorry. So this isn't really, this. Sorry, this is the mistake.
Thanks.
Yeah. Other questions? Yeah, I think that's a good point. So I have to revise the slide. Yes, this is very confusing. Okay, so now that we go to the next one. Yeah, multiple logistic regression. I mentioned a little bit, but if we have multiple variables, then we can just introduce the linear combination of x1 to xp. So left-hand side is again the probability of y is equal to 1 given the x value. So it works in the same way. And optimization, still the function is, the max likelihood function is the concave function. So it's not too super difficult to maximize it by numerical methods. Yep, so this is the case. Yeah, actually, this time that we fit the default probability on balance and income, these are numeric, and the status on whether or not the person is a student. And actually the student has the negative coefficient now, and actually the coefficient is significantly negative by this, the so-called the z-test. And the balance and income both have positive impact. The more balanced, the higher default probability. So that's pretty reasonable. And income, actually higher income, then we have higher default probability. So it's a kind of confusing, but actually this isn't really significant. So probably the income does not really matter. So balance and the status on the student matter for default probability, but the income does not really matter. Maybe higher income and higher balance, then default probability does not change much. So here we can almost see in the same way as the linear regression result, the coefficient. So this is basically the beta I hat. And this is standard error. So standard error of the beta I hat. And z statistic is the beta I hat over SE, standard error of beta I hat, or square root of variance of beta I hat. So this was originally t statistic in linear regression. In linear regression, basically the concept is that the numerator is normal and the denominator is chi-square. a square root of chi-square, then the ratio is t distribution. Ratio has t distribution. But here, since the quantities are more complicated, basically we cannot say what distribution the standard error of beta I hat follows. So we only rely on the central limits theorem. So if we have a large sample size, then approximately this is normal, and the standard error of beta I hat, we can actually ignore the variability in standard error of beta I hat. So we can assume this becomes normal if n is large. Even t-test, you can see if n goes to infinity, then t distribution with degrees of freedom n is almost normal distribution. So we just rely on the asymptotic theory. So basically, we cannot use t distribution. So we have to have more, rougher approximation than usual t-test. Then p-value is based on normal distribution. So z stands for the, z represents the standard normal distribution. So the p-value is based on, normal distribution. So for example, this one is the probability of standard normal random variable is larger than 0.37. Here, z follows normal 0, 1. So not t statistic, but z statistic. The t distribution theory does not apply. So we have only a rougher approximation than t statistic. Do you have questions? So basically interpretations are similar to linear regression. So one thing is that coefficient, to exactly understand the coefficient is a little more difficult, and the z statistic instead of t statistic. So this is another representation of the logistic regression result. So the default rate by credit card balance. So I think that this only compares at specific points. So that's why the curve is not smooth. Yeah, so, but basically the given all predictors except for balance, the default rate becomes the logistic curve. But the logistic curve is different if we think about two groups, the student and non-student. So student, they generally have the slightly lower default probability if we accounted for balance. So you can see that this graph is a little below blue graph. So if $2,000 balance and he's a student, default probability is 0.5. That is pretty high. And if non-student $2,000 balance, then probably the default probability is 0.65. So it's even larger. Yeah, relationship is complicated. You can see the difference is in terms of probability, the small around here, but the difference is more visible around here. And very high balance, probably it doesn't matter. So most people default, so default probability isn't affected by the student status. And yeah, you can imagine that we have some interaction between student status and balance. If student, actually the card balance is higher, yeah, so this is a kind of counterintuitive, but yeah, you can see, for example, the life cycle, the hypothesis. So students have potentially higher income, so even they borrow and spend. That is, reasonable in the sense that if the expected income in the future is higher, then they can borrow more. Yeah, I think in the news that I heard that the average, the student credit card balance is $3,000 at graduation. I don't know how much of those are, you know, bear interest and how much of those are just the balance without interest for the short term.
Sorry, Professor, I have a question about the previous slide. No, previous one.
Previous
no.
one.
Yeah, this one. About the, the previous one.
Previous one, sorry.
This one.
Yeah.
About the interpretation of logistic regression. Can we say by increasing 1 unit of income or balance, then the probability of default will be increased about, for example, 5% or 3%? Is that right or not?
That's not that straightforward. So this one, 0.0057. So that means the log of default probability over non-default probability. Gets larger by 0.057. So the interpretation is pretty indirect. So log of default probability over non-default probability gets larger by 0.0057. So in short, of course, the default probability gets higher. So direction is right, but we cannot have clearer interpretation than this.
Okay, but so how can we interpret these results by percent? Can we use, for example, marginals effects or odds ratio for that, or no?
So if we think about a general case, that this log of odds ratio is only way to interpret it. So if you would like to have the probability increase, then you have to set the standard scenario. For example, you plug in the average income and you fix the student status. For example, the income of maybe the $10,000 and the student status is yes. If we set these scenarios and we compare balance of $1,000 and the $2,000. So if you set this kind of the concrete scenario, then you can calculate probability for each. Then you can compare how much it increases. But otherwise, we cannot really compare the probabilities.
Okay, thanks, Professor.
Sure.
From the textbook, it says that increasing the balance of beta, that's beta 1, it increases the odds of x by e to the beta 1 for balance, but it doesn't. But it also says that the probability of x and x are not a linear relationship, so it's hard to.
Yeah, it's really hard. Yeah, so generally statistical models are not optimized for interpretation. So that's the general scheme. So yeah, it's not very easy. Yeah. Yeah. Any other comments? Yeah, so it's really hard to interpret the logistic regression result. So only sure thing is significance. So you can see the student status and the balance. Those two variables are significant because p-values are less than 0.01 or 0.05. Sorry, the another thing is that if significant, then the sign of coefficient is important. Higher balance, higher default probability. And if student status is yes, lower default risk. But except for that, it's very hard to interpret these numbers itself. Yeah. So it's not really easy to interpret this. It's difficult. Yeah. Diagnostics. So linear regression, remember that we have the regression residual plot, sorry, the residual plot, residual, and the traditionally, this is the predictor, maybe X1 or each predictor. Sometimes fitted value, but the predictor, I think it's better. And if we have some specific pattern, such as curvature, or maybe clear trend in variability, in this case, larger predictor means smaller variability, then it violates the assumption that errors are random and IID. But the logistic regression, basically yeah, it's a little bit harder to do diagnosis because the Y value is either 0 or 1. So for example, in linear regression, if we have outlier for Y, you can see that that observation is problematic. But here, the Y value is either 0 or 1. So it's hard to detect outlier. And if we make a residual plot, also the Y value is either 0 or 1. So residual plot just replicates the shape of the logistic curve. So the actually, sorry. Sorry. Yeah, so actually if we make the scatter plot for logistic, scatter plot for the residual plot for the predictors, then typically the residual plot is so like this. So this just replicates the logistic curve. So this like this. Okay. Yeah. So yeah. So think about here. So think about here, and the default, the predicted, the probability is 0.1. Then residual is either 0.9 or negative 0.1. Right. So if fitted value of logistic regression is 0.1, then Y is either 1 or 0, right? So if Y is 1, the residual is 0.9. Y is 0, then residual is negative 0.1. And X1 value gets larger, then maybe the F hat gets maybe larger, then it becomes 0.5. Then residual is either 0.5 or negative 0.5. So basically residual plots only replicates the shape of logistic curve. So it does not make much sense. So yeah, still that we can do something. So we take the average of several residuals or something, but we don't cover that in this textbook. In 6840, that we cover some interpretation of residual plots, but here that we don't do that. Because the discourse focuses more on the prediction rather than the statistical analysis, so we skip that. Yeah, and even if we have some problematic pattern, then actually we cannot really change the, we cannot really improve the situation. For example, here on the linear regression, in the linear regression, if we have the clear curvature, then you can introduce the quadratic term to improve the situation. How about logistic regression? Okay, so if we take the average of several adjacent errors, and we have some pattern, If we take average in each of these bins, then, okay, so suppose that the observations have some trend, then we have to change the logistic curve. That is hard, right? So the logistic curve is just a given. So to change it, we have to develop a new function, and yeah, so it's harder. So that's why that we don't really do the residual analysis. So this means that the appropriateness of logistic regression is largely ignored in most analysis. So use of logistic regression is motivated by fast estimation of parameters. So I mentioned that the likelihood function is concave. So that is a good property. And if we modify the logistic curve, then my likelihood function is no longer concave. So that is not good for numerical optimization. So that's why that we just stick with that function.
Sorry, yeah. Professor, I have another question.
Yeah.
But I think this is not true because we have rho square, and rho square is index for appropriateness, for goodness of fit, this model. And I'm not sure that we ignore the logistic function appropriateness. Yeah, correct?
Yeah, so sorry, you check you think about the chi-square type test for the appropriateness of logistic function?
No. Just I'm talking about rho square, index for goodness of fit, or something like, yeah, something like multiple R square for linear regression. This is an index for appropriateness. Yeah, correct.
Mm-hmm. So for what, linear regression?
No,
logistic regression.
For logistic regression. So
logistic regression. Yeah.
Yes. So we don't ignore so much. We have some index for that, but we cannot just interpret the residuals. But we have some other index.
That's right. That's right.
Chi-square test and also rho square, I think.
That's true. Yeah, so I think there are two objectives for the diagnosis for logistic regression. And one is appropriateness of the logistic curve. And another thing is the appropriateness of the model, missing predictors or something. So for missing predictors, actually, yes, there are several tests to judge the logistic regression. Yeah, so we can say that we just don't cover that in this course. But yeah, 6840, we cover whether or not the logistic regression is, the model is appropriate for the data. So we explore the possibility of missing predictors. So that is basically testing if logistic regression is sufficient. Yeah.
Okay, thanks.
Yeah, so yeah. Yeah, so maybe that we can cover a little more. Yeah, so at least we can introduce several tests on logistic regression to see if the model is sufficient or not. But we don't cover that in the course. And the next topic is what if we have multiple classes, not only 2 classes, but for example 10 classes. The character recognition problem from 0 to 9. So this is the classic example. I think that, yeah. So in 6840, so how many of you has taken 6840? I think there, I don't know. Jacob have taken it, right?
Yes, I have been in that class.
Yeah. Ian, did you take the 6840? You took 5030, right?
I took 5030 and 6840 with you.
Yeah. So then you covered the multinomial logistic regression. But Yeah, so basically the logistic regression also has the version for multivariate case. Multi-category cases. So if we have more than 2 categories, then still we can apply the logistic regression. And the method is that we set the baseline. Suppose we have k classes 1 to k, and think about the probability of y is equal to k as the baseline. And we think about the odds ratio for each of the other classes, class 1 to class k minus 1. Then this ratio can be calculated, can be modeled by this linear function. So log of odds ratio by a linear combination of predictors. So in this way, we can calculate the ratio of these k-1 pairs, and combine this with the fact that total probability is 1, that we can model the probability of each class. Yeah. So this gives the ratio. Sorry, there we go. Yeah. So yeah. So okay, so we have the k classes, and we have the k-1 ratios. Then another equation is the summation of y is equal to 1 to y is equal to k is equal to 1. So if we have this in total, so k-1 ratios and the 1 equation, so you can identify each probability of y is equal to 1, y is equal to 2, up to y is equal to k. So a problem is that there are too many parameters. So if data set is small, the coefficients are not reliable. Yeah, but still we can do that. And the multinomial function in the neural net package in R can estimate multinomial logistic regression. So neural network is basically the 2 layers of logistic regression. Neural network we don't cover in this course, but because of that structure, the neural net and logistic regression are pretty similar. So that's why the neural net NNet package includes the multinomial logistic regression. Yeah. Yeah, maybe we can mention about the neural network. So neural network, also some other machine learning method. The idea is that to make situation unnecessarily complicated, okay, then we can model very complicated situation. So that is the a kind of the idea. So think about, for example, the x1 and x2. We have 2 predictors, okay, and we think about the linear combination of this. Okay, so maybe, okay, so just ignore the intercept and the beta1 plus beta2 times x2, okay, linear combination. Then we can express slightly more complicated quantity than just simple x1 or simple x2. And maybe we prepare another linear combination, okay? Then, yeah. If we use the 2-dimensional space, then maybe we have more information. Then, okay, so we think the linear combination of this linear combination, what happens? Delta 1 times the beta 1 plus beta 1 x1 plus beta 2 x2 plus delta 2 times the beta, gamma 1. Gamma 1 x1 plus the gamma 2 x2. Okay, so it looks complicated, but anyway, this is linear combination of x1 and x2. So even if we have 2 steps, it does not become more complicated than 1 step. This is a good property for linear combination, but the 2 represent complicated structure, it's not good. In the neural network, we use logistic function. x1 and x2, we create the f is the logistic function, f of beta 1 x1 plus beta 2 x2. Then f of gamma 1 x1 plus gamma 2 x2. Okay, then we transform the x1 and x2, so it can represent more complicated situation. Then we think about the f of linear combination of these. Okay, so maybe it's too complicated, so I would say this and this. So we define this as maybe f1 and f1, and this second one as f2. Then we think about the f of maybe delta 1 times f1 plus delta 2 times f2. Then this f is logistic function, complicated function. If we use this function twice, then we create even more complicated function. So that possibly can explain the more complicated information. So that is the idea of the neural network. So they make things that unnecessarily complicated, then that we can possibly explain the more complicated situation. Yeah, and the next one, the ordered logistic regression. Before that, do you have any questions on the multinomial logistic regression? Yeah, so we don't discuss this in detail, but at least in the final presentation, the one student from the previous class will present something about multinomial, the logistic regression. So in our language, we have the two packages, NNet and the neural net package for neural network, and some other packages, maybe H2O package, H2O. So, so these are for neural networks. And this textbook does not cover neural network, and I think the main reason is that the main reason is just because of the history of the R language. So R language was developed between 2000 and 2010 mostly. And the neural network was very popular in the 20th century and after 2010. So originally, the R language isn't very strong to deal with neural network because of that historic reasons. So that's why it's missing from this textbook. So I cover it in 7810 in more details. But this class does not cover neural network. Yeah, anyway, neural network is too hot, and many other courses will cover the courses, the materials. So this course focuses on other models. And ordered logistic regression. So here we think about the case that we have more than 2 categories, but those categories are ordered. So for example, the movie rating. So 1 to 5, scale of 1 to 5, but the 2 is better than 1, 3 is better than 2, 4 is better than 3. So it's ordered. So in such a case, we have additional structure. So we have to use different methods than multiple linear regression. Multinomial linear regression. Yeah, so also we don't discuss this, but the POLR package in POLR function in the math package in R can fit this ordered logistic regression. So we assume more structure. Yes. And okay, so we use the logistic curve for logistic regression, but any other choices? Actually, the many other choices are proposed, even though logistic function is most popular. Yeah, so because the good property, the concavity of the likelihood function, and also that we have both f and f inverse in analytical form. So f is the function, f of x is equal to the 1 over 1 plus e to the power negative x. And the f inverse of x is also the log of x over 1 minus x. So it's good that both have analytical form, and it's a relatively simpler form. So that's a good thing. But also some people use other function. Instead of f, often the people use this CDF of standard normal distribution, cumulative density function of standard normal distribution. So we've seen that the link function f maps all real numbers to 0, 1, like this. So this function is naturally cumulative distribution function. And the most popular cumulative distribution function is normal, the CDF. So it's pretty natural that we use this function. But this is a little more complicated. So we have integral here, and this is exponential of negative 1/2 times t squared. So it's more complicated than logistic curve. And to make matters worse, the phi inverse does not have an analytical form. So numerically, they're more expensive than the logistic regression. So that's why the logistic regression is probably the more popular. So one advantage of using the phi of x is multivariate case. So sometimes the y is multivariate. So y is binary in logistic regression, the 0, 0, 1, 0, 0, 1, but possibly y have 2 variables. So patient is malignant or benign, and patient is satisfied and satisfied or unsatisfied. Then, so this kind of situation. So these 2 variables may be correlated, but the different variables. So in such a case, that we use the multivariate logistic regression model. So in this case, this is good because the normal distribution is good at dealing with the situation of multivariate case. So think about the the random variable x1 and x2. The both follows some distribution. For example, some distribution implied by the logistic function. So suppose that the logistic function is CDF, then x1, x2 follows those CDF. Then a times x1 plus b times x2. This does not follow logistic regression, logistic distribution anymore. But the normal case, if x1 and x2 are normal, and these are independent, this is independent symbol, then ax1 plus bx2 follows normal again. So normal distribution have good properties for multivariate case. So multivariate case, actually the phi of x is actually a better function to use. So theoretically, you can fit the model with logistic curve and the normal CDF, then choose the better one. But usually people don't care too much about it. And this is the regression model with this normal CDF is called Probit regression. And the practically biggest difference is the tail part. Yeah, so this part. So logistic curve, the convergence is slower. So if we make the logistic CDF, so it's pretty similar, but finally the convergence is slower. Okay. So that means the probability does not approach to 1 fast. That is sometimes good if we have outliers. If we have one outlier and the probability is very high, but actually it fails, then basically that observation almost determines the entire likelihood function. So that is problematic. So if we have outliers, logistic regression performs more stably. So in some sense, it's good. Which is good? In general, we don't have any answer. It depends on the data. Logistic regression is more robust and slightly less efficient, often. And yeah, so that's some topics on logistic regression. Yep. Any questions so far? Yeah, just it's good to know that there are several versions of logistic models. When logistic regression does not work, then you can just remember my slides, then you can explore some other models. And linear discriminant analysis is the next topic. So the linear discriminant analysis is often the more stable than logistic regression. So one big problem in logistic regression is it's unstable when classes are well separated. So it's a kind of counterintuitive. If data is good and separable, then actually the model is unstable in logistic regression. The situation is like this. So we have, suppose, x1 and x2, two predictors. And we have the scatter plot and logistic regression. So we have binary y. So one class is here and another class is here. So it's well separated. And logistic regression is basically make a straight line between this and think about the score. That we think about the linear combination of x1 and x2. So that is basically that we consider score along this vertical line. Then we fit the probability. So such as, okay, so we fit just as an image, we have this kind of probability. So suppose we have one observation, then we think about the vertical line, then we think about this point. So this point has the score, and this score corresponds to this probability. And maybe this is probability 0, probability 1. So this is probability 0.8 or something. So logistic regression determines the parameters, but basically it determines some line. It determines some line. And we think about the score of each observation on this line. Then depending on the score, we calculate the probability. So that is logistic regression. And this has sometimes problem when data is too good, because if two groups are separable, actually another line, maybe this line, also perfectly, separate the two classes, or maybe this line also perfectly separated these two groups. So actually we cannot really, determine which direction is the best direction to separate these two groups. So that's why the logistic regression becomes unstable when data are separable. So data are separable, that is a clearer situation. So it should be easier to, separate two classes. But for logistic regression, sometimes it's more difficult. And LDA does not suffer from this problem. So LDA basically focus on the center of these two groups. So the center of these two groups are maybe around here and around here. So of course, if distance is larger, it's better to distinguish these two groups. So that is the idea of linear discriminant analysis. So think about the center and the distance from the center. Then we determine which class each observation belongs to. Yeah. Yeah, and to be exact, that we use the Bayes theorem to identify that this probability that each predictor value that belongs to the which class. Yeah, so the an example. So want to classify the animals into horses, the giraffes, and the deer. So we have 3 groups. Maybe class 1 and class 2 and class 3. And the yeah. So the linear discriminant analysis, they think about the problem in the other way around first. So we approximate the joint distribution of predictor variables, the weight, height, and neck length for each species. Okay, so originally we observe X. Original problem is we observe X and we decide that which class that animal is in. Okay. So X2, C1, C2, C3. But at first, LDA, they think about given animal that we consider distribution of X. So what's the distribution of weight, height, and neck length for horses? What's the distribution of weight, height, and neck length for giraffes? For example, the giraffes have longer neck length, so average of 3 meters and the standard deviation of 1 meter. And the height is between maybe 5 and 10 meters. And weight is, I don't know, the 2,000 pounds plus minus 500 pounds. So we think about the distribution for each animal. Then after that, using Bayes theorem, that we calculate the probability that animals is horse, a giraffe, or a deer by using X. So at first we start with this, then finally we calculate the given X, we calculate the probability of C1, probability of C2, probability of C3. Yeah, so at first, just a review of Bayes theorem. So the probability of A given B, A and B are events. So events is mathematically the subsets of entire probability space. Yeah, so events. And probability of A given B is equal to probability of A times probability of B given A over probability of B. So basically this is the rule to calculate probability of A given B from probability of B given A. And the proof is clear if we think about, okay, so we multiply P of B on both sides, then you can see each side is just probability of A intersection B. So that is the definition of the conditional probability. And the other side, just A and B flips. So still the probability of maybe B intersection A, I would say, but that is same as this. Okay, so now that we use this Bayes theorem to calculate the probability of an animal belongs to the case class given the measurements from the other one. So probability of X given Y. So yeah, so Y have the 3 classes and the X is just continuous measurements such as weight and height and neck length. Okay, so probability of the Y is equal to K given X is equal to X by the definition of conditional probability, that this is this. So probability of, in general, the event A given B, that is the probability of A intersection B, probability of B divided by probability of B. So this comma is intersection, right? So X is equal to X and Y is equal to K. Okay, so now the second line. So x is equal to x, but the So so this is this is in general the true. So the x is equal to x and y is equal to k. So that is at first y should be equal to k. Then given that condition, that also x should be equal to x. So this is always true. So probability of A intersection B. This is always probability of A given B times probability of B. Okay. Yeah. Maybe the other way is more consistent, maybe. But anyway, so it's the same, but maybe B given A. Oh, sorry. B given A times probability of A. Anyway, so so in general, that is true. And the denominator. So denominator is what? The probability of x is equal to x. Okay, so there are k different cases. So we don't know the value of y in the denominator. So think about each case. The y is equal to L. And given that y is equal to L, the probability of x is equal to x. So this is, okay, so sorry. So this is at first. So this is at first the summation of the probability, summation of probability of x is equal to x and the y is equal to L. And L is unknown, so 1 to k. Then x is equal to x and y is equal to L. So this is also represented as this. Okay. Yeah. So if we know this quantity, so this probability of y is equal to k and the probability of y is equal to L, then we can calculate this. So we defined the pi k as probability of y is equal to k. Then that we can calculate this. So now that we have the way to calculate this y given x by x given y. So we can flip the relationship between x and y by this equation. Yeah, so this pi k matters for the probability. So that means, okay, so the deer and the giraffes and the, sorry, the deer and the giraffes and horse. Okay, so horse. Okay, so suppose the 90% of the animals in the population is horse. So that means that if the neck length is slightly larger, still we believe that that may be a horse because the most animals in the class is horse. So that the prior probability that matters. When I lived in Wisconsin, often I was asked if I'm a Korean. So I'm Japanese, but I was often asked by the strangers whether you're Korean, and that is a reasonable question in Madison, Wisconsin, because in Madison, Wisconsin, there are a lot of the Korean students, and the Japanese students, they're much smaller, has a much smaller population. So in that case, okay, so even if the people are not sure that this guy is a Korean or Japanese, still, okay, so Madison have many Koreans and very few Japanese, then it's, the more likely that this guy is Korean. So that's why they asked me, there was a, are you Korean? And that is, in the Bayes theorem perspective, the pi sub-Korean is larger than the pi sub-Japanese. So that's why the people, they guess this guy is Korean. So the pi k, the prior probability matters for the the posterior probability. Yeah, so the probability of y is equal to L is called the prior probability because we haven't observed x. And this is called the posterior probability because the probability after that we observed x. Any questions? Yeah, so the linear discriminant analysis, the assumption is that the probability of x given y, probability of x given y is represented by Gaussian distribution. So f sub k of x, if the class is k, the distribution of x is this. So normal distribution. So one variable case, this is just the univariate normal distribution, and the multivariate case, that is just the multivariate, the normal distribution. So x may be a vector. So in such a case, the mu k is a vector. So here, weight, height, and the neck length. So x is three-dimensional vector. The mu k is also the three-dimensional vector. That is possible. Yeah, but for now, maybe you can think about just the univariate case. And the linear discriminant analysis also assumes that the sigma k is the same for all case. So the distribution is the same for all observations. The variance is the same for all observations. Yeah. So that makes the situation simpler. And if you use the Bayes theorem, then the probability of k of x is this. So this is the probability of y is equal to k given x is equal to x. Okay. This is x. So this probability is given by this. So pi k, and pi k is the prior probability, and times this over this. And the Bayes classifier that assigns the class k to x so that pk of x is largest among this. So basically this means, so this is the distance from the between x and the mu k. So basically if we observe x, that observation is classified to the nearest class. So if x is closest to mu sub k, then that observation is classified to k's class. So that is the rule of LDA. And the LDA, actually, the boundary is the linear. So if we have the x1, x2, and we do linear discriminant analysis, and then mu sub 1 is here, and mu sub 2 is here, then boundary is linear. And just the separating line between mu1 and mu2. So that's why we say this as linear discriminant analysis. So this is just the simplest case that the slide discusses. So suppose we have k is equal to 2. So we have the two classes and the one-dimensional case. Then what happens? Then the boundary between class 1 and class 2 is just the midpoint of mu1 and mu2. So if the class average for class 1 is mu1 and class average of the class 2 is mu2, then just the midpoint of mu1 and mu2 is the boundary. So if x is below, so suppose the mu1 is smaller than mu2, and if x is below this midpoint, then that observation is classified as the group A, class 1, and the class 1. And if larger than that, then we classify that observation in the class 2. Yeah, so to be exact, you can see that this is the delta k is the log of f sub k of x, and this is true for k is equal to 1 and 2. Then just we think about the boundary so that the value of delta kx and the value of delta 2x is the same. Then we get x is equal to mu1 over plus mu2 over 2. Because this part basically disappears. This part does not involve x. So basically we equate this for k is equal to 1 and k is equal to 2. So 1 over 2 sigma square x minus mu1 square is equal to 1 over 2 sigma square x minus mu2 square. Then the 2 sigma, it does not matter because it's the same. So we just cancel, and x square term cancels. So then we get the maybe negative the mu1 x. Also we multiply negative sign. So maybe it's positive. So positive maybe 2 times mu1 x and minus mu1 x square, right? And 2 times mu2, maybe 2 times mu2 minus mu2 square. So we solve this, then x1 is equal to, x is equal to mu1 plus mu2 over 2, right? Just move several terms and simplify, then we get this. Yeah. So this is the basic idea of the linear discriminant analysis. So this is the case of the f1 of x, and this is f2 of x, and here x. And you can see the variance, it has the same size. The widths of these two histograms are the same. And so this is based on the assumption of sigma 1 square and sigma 2 square are equal. And this assumption is often useful because otherwise it's the counterintuitive situation happens. So suppose that the sigma 1 square is larger than sigma 2 square, then what happens? Then this green distribution gets much flatter like this. Okay? If sigma 1 is much larger than sigma 2. Then, okay, so maybe around here it's fine. It's more likely to be in the class 1. And around here, it's more likely to be class 2, but it's fine. But actually, if x gets much larger around here, so again, the value of f1 is larger than f2. So this is counterintuitive, right? So it's the situation such as if neck length is much larger, then it's a giraffe. But neck length is even larger, then the observation is again classified as a horse, something like that. So it's pretty complicated situation. So the sigma 1 is equal to sigma 2. That is often, the inappropriate and a good restriction. Yeah, so that is the linear discriminant analysis. So next time that we continue to discuss linear discriminant analysis further.